Hey guys, here is the first part of your chapter 7 lecture. This is when we're going to actually start to talk a little bit about quantum mechanics, how atoms are made up, and how electrons work. Okay, and we're going to start off by talking about Schrodinger's cat. Okay, some of you may have heard of this before. It involves a cat that's in a box. The box has some poison in it. It's kind of a messed up experiment. This is the basics though, okay? So you have the cat, you have the poison, and you have this radioactive source, and they're all placed in a box, and the box is sealed. So if the little radioactive source in there starts to give off any actual radioactivity, then the monitor attached to the box is going to shatter the flask. The flask will release the poison. The cat will die. Okay? But none of us knows what's happening inside of that box. So once the cat and all this stuff is sealed into the box together, the cat is dead and alive at the same time. Right? Until someone observes what's inside the box, we can't tell whether one thing or the other thing is true. Okay? But once we observe what's in the box, that's when we can determine that we don't have a situation where the cat is both dead and alive. It's an either or situation. Okay? It's a really weird thought exercise, but it kind of sums up how electrons work to the best of our knowledge right now. Okay? These drawings are from Pia. They're kind of lovely. Okay, there's your cat. You don't know what's happening to him right now. Has the detector gone off yet? Has the flask cracked? Is the poison leaking out? Without physically observing what's happening inside the box, there's like a 50% chance that either thing is true. Okay? Only once you open the box up and look at the cat, that's when you have an answer to your question. Okay, the act of observation is what forces your system into one state or the other. Okay, so your cat is either dead or alive. It's not both, right? This Schrodinger's theory, it's very useful when you're thinking about things that are extremely tiny, like electrons. The word quantum means very, very small. And when we talk about quantum particles, we're talking about things that have a dual nature. So things that can exist in two states at the same time. Again, it's a weird concept to wrap your head around at first. Electron behavior, as we've talked about before, determines most of the behavior of atoms, the chemical properties of atoms, things like that. But we cannot observe electrons in an atom. They're so small that when we observe them, like the Schrodinger's cat equation, it changes the behavior. It forces something to happen. So we can't even take a look at what the electron does in nature. So we use a quantum mechanical model to try to explain some of the behavior of electrons and subsequently of atoms. One of the properties of an electron is its wave property. Light in general travels in waves. Okay, it's one of its travel methods. And light's a form of electromagnetic radiation. Electromagnetic radiation is radiation that has two different fields that it's traveling in. Okay, so it has one field that's an electric component. Okay, so you see it operating like this, but it also has a magnetic component to it. That magnetic component also travels in wave form, but it travels at a 90-degree angle to the electric field. All right, so that's what this phrasing up here means. It's composed of perpendicular oscillating waves. So the waves are going up and down, and the two waves are at 90 degrees from one another. And one wave is the electric field, and the other wave is the magnetic field. And all of these electromagnetic waves, which is the combination of those two, they move through space at the speed of light, which is 3.00 times 10 to the 8 meters per second. Okay, and that's a lot faster than something like the speed of sound, right? So a good way to differentiate this in your own head is thinking about when you look outside during a thunder and lightning storm, how you can see a flash of lightning, but you don't always hear the thunder right away because the light is traveling much faster than that sound the thunder makes. But we have to talk about some of the characteristics of waves themselves, right? Because we're going to use these characteristics of waves to figure out information about the light, about electrons, about the energy involved. All this is important. So what we have over here, this is a wave, okay? So this is just one of the waves that's in our electromagnetic field. The top part, the highest point here, that's called the crest of the wave. All right. This flat line here, the central plane of it, that is called the node. All right. A node is like it says down here, it's a 0 point on the wave. Then the lowest point on a wave is called the trough. All right. So we have the crest, we have a node, and we have a trough. And we are going to measure a wavelength of a wave from two similar points in the wave cycle. So if you measure the distance between one crest and another crest, that is a wavelength. You could similarly measure one node intersection to a second node intersection. That could also be one wavelength. Or one trough to another trough would be another. That would be another example of measuring a wavelength. Okay, but you're measuring the actual distance that the wave travels in that period. The frequency of a wave is the amount of waves that pass a certain point in a given amount of time. Okay, so if we look back here, say that this is my point. I would want to know how many waves pass through this point in maybe 30 seconds. Okay, however many times a wave would pass through this point in 30 seconds, that would be my frequency. All right. The symbol for frequency is this. It looks like a drunk V. Okay, because it's not a regular V. That stands for velocity. It's this weird tilted V. The units for frequency are inverse seconds, which is seconds raised to the -1, or 1 over seconds. And an inverse second is also equivalent to 1 hertz. So hertz is frequently a unit that's used when talking about frequency. And these two factors, wavelength and frequency, those determine the color of the light that we see. Okay, everyone knows what our spectrum, our color spectrum looks like. When you put white light through a prism, it separates out into our standard rainbow of colors. Each of those colors is associated with a particular wavelength of light. Okay. Now it is important to note that whatever color we are actually observing is the color that's being reflected after an object absorbs the complement. Okay. So when we are seeing something like the color blue, that means that the color orange, or the wavelength associated with orange, is what's being absorbed by the object we're looking at. So today I'm wearing a red shirt. That means that my shirt, when the light hits it, it's absorbing the green wavelength. Okay, so that what everyone sees is this red color. All right. And different wavelengths correspond to different colors. So very long wavelengths, very long wavelengths, like what's happening up here, those are associated with more red colors. Very short wavelengths, like what's happening down here, those are your blues and your violets. And again, we're noticing the wavelength based on the distance between two crests in this case. That's the easiest way to look at it. So the distance between these two crests is very large. The distance between these two crests is in the middle. The distance between these two crests is very small. All right, so that difference in wavelength, that corresponds to a difference in color. Now, the amplitude of the wave is the height of it. Okay, so you see the height from the node to the crest here and the node to the crest here. The amplitude of the wave is associated with its brightness. Okay, so something with a very small amplitude is going to be a dimmer light than something with a very high amplitude. So take a second and read over this question and try to answer it. Think about what we just talked about in terms of color and wavelength and amplitude specifically. If I have a bright green laser and a dim red laser, what does that mean in terms of the wavelength of the light? What does that mean in terms of the amplitude? Okay, so the two lasers, hopefully we are on the same page that they would have different frequencies and different wavelengths, right? Because things with a very, I should actually go back and show you that again, but something with a very long wavelength is going to have a smaller frequency. Something with a shorter wavelength will have a larger frequency. So if they have different colors of light, then you have light that is at different wavelengths and also different frequencies. If you have a difference in the dimness versus brightness, then the brighter light has a greater amplitude. But before we move on, I just want to go back here so that we can talk about, because I didn't specifically say that. I want you to imagine that these light, all of these wavelengths are moving in this forward direction, okay? And for 30 seconds, we are going to track the light as it passes. Let me draw a line here. This point. Okay, 30 seconds. I'm going to track how many full waves pass that point. It should become clear that this first wavelength, the longest wavelength, it's going to intersect this point many fewer times than something like this blue wavelength, right? This blue wavelength is so short that it's going to pass by this point many, many times. So things with very short wavelengths have very high frequencies. Things with very long wavelengths have very small frequencies. They're inversely related. So I guess I could have saved it over here, but you know, seeing it visually I think is a little bit better. What that does lead us into is a way that we can use the speed of light to figure out what the frequency and the wavelength of our light that we're looking at is. Okay, so this is one version of our standard frequency and wavelength equation. So the frequency of any light is equal to the speed of light divided by wavelength. And important things to notice is that your frequency has to be measured in hertz, regular hertz, no prefix on that, or inverse seconds, those are the same thing, and your speed of light has to be measured in meters per second, and your wavelength has to be in meters. All right, so all of those units have to be matched up in order for them to cancel out and for you to calculate the correct thing. Okay, so let's try this. All right, calculate the wavelength in nanometers of the red light emitted by a barcode scanner that has a frequency of 4.62 times 10 to the 14 inverse seconds. All right, so this should be pretty straightforward. You're going to write out your frequency wavelength equation, and you're going to plug in the values that you know. All right, so this is our standard equation right here. And we want to solve for wavelength in this case. So we have to rewrite the equation and solve it for wavelength. Once we do that, we're going to get a value, and that value is going to be in meters. Visible light is almost always reported as a nanometer value. All right, so you have to be very comfortable taking this wavelength that's in meters and then immediately converting it into nanometers. All right, so make sure that you practice this conversion. Don't let it confuse you. Okay. When we're talking about the electromagnetic spectrum, that's going to include every wavelength, from the longest wavelengths to the shortest. And on both ends of that spectrum, there is a lot of radiation that we do not see. All right, we can only see a very small amount of the electromagnetic spectrum. The shorter wavelength light, which has the very high frequencies, that light has a higher energy. So the greater the frequency of light, the greater the energy associated with it. Also, the higher the energy, the more dangerous the radiation is. Okay, so at the low end of our energy spectrum are radio waves. So radio waves have the longest wavelength and they have the lowest energy. At the other end of our electromagnetic spectrum are gamma rays, which have the shortest wavelength and subsequently the highest energy. All right, so take a minute and try to do this. Which group of types of light is listed in order of increasing frequency? So increasing frequency means the smallest frequency to the largest frequency. All right, so the important thing to do here is to make sure that you are connecting frequency back to energy level. Okay, so if I want to go from the smallest frequency to the largest frequency, then I'm going from the lowest energy to the highest energy. So when you look at your electromagnetic spectrum, you should see that infrared has the lowest energy out of those three options, and ultraviolet has the highest energy. All right, and speaking of the electromagnetic spectrum, this is a visualization of what it looks like. And you should have the order, this order, memorized from radio to gamma. You do not have to have all of the individual numbers memorized, but you should absolutely be able to list these in order from smallest to largest, and vice versa. I'm going to draw a little bit on here just so I'm going to order them starting with 1 for the lowest. Then microwave is going to be 2. Infrared is 3. And then over here, right here, that's your visible light. That's in between infrared and ultraviolet. Okay. Now, what the book has done has taken this little section over here and it's blown it up so that you can see, you can visualize what's happening within that that very small area. All right. So it goes from 1, 2, 3, 4, and then within the 4, this is the low energy, and this is the high energy. Okay. Then there's 5, 6, and 7. Now this red light, it's up against the infrared section. This violet light is up against the ultraviolet section. And that's how those two sections get their names, okay? Because you're going from low energy to high energy. So you're in this infrared section, and then right at the end of the infrared section, now you can start to visualize the red light. Now we're into the visible range, and we stay in that visible range up until we're in the violet section. Then when we're when we pass like the energy threshold that we can't observe it anymore, now we're in the ultraviolet region, or above energy that's even above the energy of violet light. Oops. Another property of waves is wave interference, all right? And that is any interaction that happens between two waves. So interference can be additive or subtractive, all right? Now we have what's called constructive interference here. That's when waves are interacting in phase. In phase means that these crests match up, right? So you see how the crests are happening at the same time? Those waves are in phase, or they're mimicking each other. They look like they're the same wave, basically. When you have two waves that are in phase, the waves add on to each other, and they make one wave that's a bigger wave. Okay, so the crests over here, they added together to make a really big crest and a really big trough. That's constructive interference. You're building up a bigger wave. The opposite of that is destructive interference. This is when you have waves that are out of phase, or their crests and their troughs are matched up together. What happens when you have a crest and a trough that's matched up together is that they're not building on each other. Instead, they're kind of destroying each other, right? That's why it's called destructive interference. Instead of having bigger waves, you end up with smaller or no waves, because the crest of one hit the trough of another one and they canceled each other out. And that's what keeps on happening. They keep canceling each other out every time they interact. So what you end up with in terms, like why you need to know this is because when you have destructive interference, you end up with a dimming effect, okay? Because destructive interference is going to cause smaller amplitudes or no amplitudes, right? Where you have constructive interference, now you have these really high amplitudes. Well, now you have brighter light that's happening, because our dimness is, or our brightness is related to the amplitude of our waves. Another property of waves is what's called diffraction. Okay, and diffraction, so they're talking about these, like you're supposed to imagine that each of these lines is the crest of a wave. When a wave hits something, when it hits a barrier of any kind, all right, and that barrier has a small opening in it, the waves don't travel straight through, okay? When they hit this opening, waves tend to bend around the barrier, okay? Depending on how quickly they are moving, they will bend to a greater or a less degree. But that diffraction is an actual bending of the light, right? Waves diffract. Particles do not diffract. A particle, if it hits this opening, is just going to keep on traveling straight through. But when a wave hits an opening, it's going to bend around that opening and start moving in a different direction. So what you're seeing here is an example of both of those things. This is light that is being diffracted, and you'll see that you have this spreading out based on wavelength. Okay, and that's opposed to the beam effect that goes straight through. So you see the spread of color here, Okay, and again, the spread is based on the different wavelengths, which is based on speed. And then you have the particles that are moving straight through. They're not bending around the opening. Okay, you can also affect the angle that light is diffracted by changing the size of the opening it's moving through. So things with a very small opening are gonna have a much higher angle, right? Or a much sharper angle. So it's gonna be going like this, and it's gonna make a really hard turn here. The angle on a large gap is a lot more of a gentle bend. Okay, so we have a really severe bend over here and a much more gentle bend with a larger gap. And waves create what are called interference patterns when they're diffracted through these slits or these openings in a barrier. Okay, so when you see one of these interference patterns, what you're seeing are alternating views of places where you had constructive interference, which are these bright spots, and places where you had destructive interference. Those are the blacked out dim spots. All right. So the way the waves are interacting with each other will form a particular diffraction pattern based on the points where the waves were in phase versus where the waves were out of phase. So our waves were in phase on all of these areas that are bright, and they're out of phase wherever we have these dark spots. We can start to focus in a little bit more on electrons now. And what we have, what we see when we're looking at electron behavior is that metals tend to release electrons when you shine light on the metal surface. Okay, that release of electrons is called the photoelectric effect. We have, I mean, I guess you would imagine, right, that if you have a very, very high intensity light, that you would be releasing many, many more electrons, right? Like the more light you put in, or the more intense the light you put in, the more electrons you would be, you'd just be able to like release more and more and more over time. You would also imagine that if you had a very dim light, that you could eventually store up enough energy, and eventually a very dim light would absorb enough energy, or the metal would absorb enough energy from it to release an electron. Okay, that's not how it ends up working. All right, there's what's called a threshold frequency, which sounds complicated, but it actually makes a lot of sense. There's like a minimum energy value or a minimum frequency value that any light needs to be at before it is able to eject an electron, basically. And the best way that you could visualize this is this example from your textbook where they were talking about imagine that you're looking at a window, okay? And if you break the window, that would be equivalent to ejecting an electron from a metal surface. Okay, and so you have this very dim light, and that dim light would be represented by ping pong balls. All right, now you take a ping pong ball and you throw it out the window, and it's just going to bounce off. Okay, so that would be equivalent to your metal surface trying to absorb energy from dim light. Now, it doesn't matter how many ping pong balls you throw at the window. It's never going to add up to enough energy to break that window. Just like with that dim light, it's never going to have enough energy to reach the threshold frequency and eject your electron. With that same kind of analogy, you can imagine that if you had this high energy light, right, we can imagine that as a baseball. Now, if you throw a baseball at the window, you're going to break the window, right? So there you go, you've ejected your electron. Now, it doesn't matter whether you throw one baseball at the window or whether you throw 25 baseballs at the window. You know, your electron has already been ejected. So that's the idea of that threshold frequency. Like, you hit this one point and you're going to either be able to eject the electron or not. Okay. And this behavior of electrons is not what people expected, right? Because people had spent a long time describing electrons as wave particles. This is the first time where someone looked at the behavior of light and started to think, well, maybe it doesn't work exactly like we thought. Einstein actually proposed the idea of these little packets of light energy. He called them photons. And he said that the photons of light are going to be proportional to the frequency, or the energy of the photons of light will be proportional to the frequency. So energy and frequency are going to be directly related, just like we already discussed, and the energy would be inversely proportional to the wavelength. Okay. Now this idea is represented by a new equation, which is, you know, it's always annoying because you guys have like, you're going to have a whole bunch of different equations that essentially say the same thing, but you have two new versions of an energy equation now. Because you have the energy of a photon is going to be equal to Planck's constant times the frequency of the light, or energy of a photon is going to be equal to Planck's constant times the speed of light divided by, I think that. Wait, pause here. Okay, I had to fix that slide. Because you see it had, oh Jesus, I still have it messed up, hold on. Gonna fix this for you guys eventually. Okay, for real, I got it this time. If you look back at what I had written, it was like HC over frequency again, which doesn't make any sense. So anyway, your two energy equations are going to be Planck's constant times frequency, and then Planck's constant times the speed of light divided by the wavelength of light. These two equations are the same equation though, all right? Because if you remember how we defined frequency and wavelength before, frequency is just the speed of light divided by wavelength, okay? So these two energy equations are basically, one of them uses this and one of them uses this, but you're either multiplying Planck's constant times this, or you're multiplying Planck's constant times this. And Planck's constant is this value here, which you have to know, 6.626 times 10 to the negative 34 joules times seconds. Now, we already talked about what a joule means when we talked about chapter 5 and our kinetic theory of gases. So you guys should remember that a joule is equal to kilograms times meters squared over seconds squared, right? This thing down here. Hopefully that thing goes away in a minute. So another unit that Planck's constant has is kilograms times meters squared divided by second. All right, these two things are the same. They're the same value written in slightly different ways. Okay, but it's very important to be able to use them interchangeably depending on the information that you're provided with. All right. Let's look at an example of what we would do, you know, with a question asking about some of these things. A nitrogen gas laser pulse with a wavelength of 337 nanometers contains 3.83 millijoules of energy. How many photons does it contain? All right, so the first thing you want to do is ask yourself, what do I need to find out and what do I already know? Okay, now I know I put up a lot of this information at once, but let's just talk through it. First of all, I know that the wavelength is 337 nanometers. And I know that whatever formula I end up having to use, I'm going to need this wavelength in terms of meters, because all of my equations require that my wavelength unit is in meters. Right? So the next thing I'm going to say is, all right, well, it gave me an energy value here, an energy value in millijoules. So maybe a good plan of attack would be figuring out how much energy one photon of light would have at this particular wavelength. Because we should keep in mind here that these two formulas, this is the energy of one photon of light. This is the energy of one photon of light. All right? So now I can find the energy of one photon of light at this particular wavelength. So I'm going to plug Planck's constant in. I'm going to multiply it by the speed of light, and then I'm going to divide it by my wavelength in meters. And it turns out that one photon of light is going to be associated with 5.8985 times 10 to the 19 joules. All right, I know that my laser pulse contained 3.83 millijoules of energy. So now I can say, well, I had 3.83 millijoules of energy. First, I'm going to turn that into joules. So my unit here looks like my unit here. All right, so that's the step that happened right here. Now I'm going to say, well, I had 3.83 times 10 to the 3 joules. I'm going to divide it by the number of joules that would be from just one photon. And when I do this, I will figure out how many photons were responsible for this particular energy value. Okay, so in this case, they gave us a formula to use to solve this problem, but you don't necessarily need the formula itself. You know that you have 3.83 times 10 to the negative 3 joules total. And if I divide that by the amount of energy associated with each photon, the answer would be the number of photons that are present. Does that make sense? Like if I said I had, I don't know, 30 joules and every photon gave off 5 joules, how many photons do I have? I'd say, well, I'm going to take my 30, my total, I'm going to divide it by 5, which is the joules each photon gives off. 30 divided by 5, I must have had 6 photons. Okay, that's all we're doing right here. There is particular energy that is associated with an electron as it's still held to the atom. That's called the binding energy, and it's given that fancy little symbol there. Okay, so when your H times V value, when your energy value equals your binding energy value, that is when your electron can actually exit the metal and be emitted. Okay, this is the value that you're trying to get to in order to cause the electron to be ejected from the metal. Now, usually you don't just have exactly this much energy. Usually you have more than that. And whatever the difference in energy is, that becomes associated with the kinetic energy of the ejected electron. So if you have something with a very high frequency, right, you're going to have something with very high energy. So something with very high frequency is going to have a lot of extra kinetic energy when it leaves the surface of the metal. And you can figure out what the kinetic energy is because you can get that HV value, right? You can take the frequency and Planck's constant, calculate the energy of the photon, and then you can subtract the binding energy from that value. The leftover energy is the kinetic energy of the photon. Right? So let's think about a little thought question here. Suppose a metal will eject electrons from its surface when struck by yellow light. What will happen if the surface is struck with ultraviolet light? And these are your options. Okay, read through them. Pause this a second. I'm going to move on, but pause it and read it and try the question out. Try to reason it out. Okay, why is this true? Electrons would be ejected, of course, because the wavelength of ultraviolet is lower than yellow, which means its frequency is higher. So it's definitely going to meet the threshold frequency of the metal, right? It's the threshold frequency can be met with yellow light on this particular metal. So whatever the frequency associated with yellow light is, that's our minimum value. So we're hitting it with ultraviolet light, that's a much higher frequency. Now, a higher frequency means that when we do our energy equals Planck's constant times frequency formula, our energy value is going to be much larger than if we use the frequency of yellow light. So the subtraction here, our kinetic energy value, the energy of our photon associated with ultraviolet light would be a much higher energy than the energy associated with the yellow light. So when we subtracted these values, and the binding energy would be the same for the electrons in both cases. So when you subtract these numbers, the kinetic energy associated with the ultraviolet would be greater than with the yellow, right? Okay, think this one out. Okay, this is just a little bit of math. All right. Hopefully that makes sense. Try this one. So we're doing, it's like 3 parts here, okay? You have 3 types of electromagnetic radiation, your visible light, your X-rays, and your microwaves. And you're gonna order them from smallest to highest of each of these things. Okay, you gotta be able to do this for this chapter because it's like an easy task, but if you're not constantly reminding yourself the order, it can get confusing and you don't want it to. So in order of increasing wavelength, that's smallest wavelength to largest. Okay, for frequency, smallest frequency to largest frequency. You've got to think about what those things mean. So first of all, with the wavelength, your X-rays here are going to have the shortest wavelength because they are the most high energy. The visible comes next and then the microwaves. For frequency, the opposite is going to be true. Microwaves are going to be less frequent than the visible waves, than the X-rays. And in terms of energy per photon, that is going to decrease with increasing wavelength. So again, the smallest amount of energy per photon is going to be associated with the microwaves. The largest amount of energy is going to be associated with the X-rays. All right. We talked a little bit about the spectrum before, okay, but that was more of like, I don't know, our normal definition of spectrum. Each element or each atom has its own particular spectrum that's associated with its own components. Okay, we can look at what are called emission spectrums of your elements, and they're going to actually produce patterns of light that are repeatable and are specific to that particular element. So for example, anytime that you have a hydrogen sample, okay, and you're shining a hydrogen light through, this is like one of the diffraction slits over here. Now, once the light moves through the slit and then hits this prism, that prism is going to separate out the light into the corresponding wavelengths, so that every hydrogen spectrum is going to give off these 4 particular lines of light. Okay, so an emission spectrum is showing you the light that is emitted by the particular element, and it is going to be specific to that element. An emission spectrum is not the only type of spectrum. Okay, you have your continuous spectrum that is produced when all of the colors are present. You also have what are called absorption spectrums, which I have a picture of in an upcoming slide, so I won't jump the gun there. You should know that whenever the atoms or elements, molecules, whatever they are, whenever they absorb energy, they're going to have to release that energy as well. Okay, so they're able to release it in the form of light, and some of the best stuff that we get to look at as like people has to do with that. So when we're looking at fireworks, when we're looking at neon lights, we're looking at that release of light energy. Okay, now what we looked at before, the emitted light passed through a prism, that's when you can get a pattern of wavelengths unique to the element. They're what's called non-continuous. So this is continuous. This is non-continuous because you have the separation of each of the particular colors. And not all colors are going to be present in every emission spectrum, obviously. For hydrogen, there were only those 4 colors. These emission spectrums can be used to identify a material. You can also do flame tests to identify material, because when you burn something, the color that's associated with the flame it produces is specific to the element. Now, flame tests are not as specific as something like an emission spectrum, because the emission spectrums have more points of reference that you can compare it to. A flame test just has one color that you're looking at. Okay, so here is some examples of these. This is the color of the neon lights that are associated with the particular elements here. Okay, and obviously fireworks is an example of that. And this is an example of what an absorption spectra would look like. So you see with the emission and the emission spectrum are the black backgrounds and then the different color lines. The absorption spectra have this continuous spectrum here, and there are white lines present wherever characteristic wavelengths from that element would appear. So you can use either an emission or an absorption spectrum to identify an element. They'll both tell you the same information, it just looks a little bit different. If you were looking at the absorption spectrum for helium, you would see the gradient from violet to red, but everywhere that you see like a blue line here, you would see a white or a light colored line in place of the colors that you see here against the black background. So I think that a lot of times the emission spectra look cleaner and more easily identifiable, but you can get information from both types of spectra. Here is an example for mercury of both types. Okay. And these are some classic flame test examples. So you see, like, they're distinct. It's just that, you know, there's a lot more subjectivity to identifying an element with a flame test versus being able to look at these bands of light or dark. And I don't know. That's what it seems like to me anyway. We're going to talk now about Rutherford's nuclear model as we're moving into more of the calculation portion. So mostly we have, this is the stuff we talked about before. We have an atom. In the center of an atom, there's the nucleus. The electrons are going to move around the empty space in the atom. All of our electrons are going to be constantly moving and negatively charged. But the theory is that as electrons sort of exist and they're moving around, they should technically lose energy. And eventually they should start to sort of slow down and maybe crash into the nucleus, and eventually atoms should collapse. But that's not what happens, okay? And we had to figure out some kind of explanation that accounted for the reality of the situation. So Bohr came up with this model of the atom and said, well, I think that the amount of energy that's in an atom is going to be related to where the electron is positioned inside of the atom. All right. So the atom is going to have these very specific amounts of energy associated with it. Electrons are going to travel in orbits that are in a fixed distance from the nucleus, or proximate orbits. Okay, because that's not it's not exactly like a planet orbiting the sun. But it's close enough to think of it that way. The electrons are going to emit radiation or release it when they transition from a higher energy to a lower energy level. And if they transition from a lower level to a higher level, they're going to need to absorb energy. Okay, and this is an example of what the orbitals, the electron orbitals, would look like. Right? I guess not orbital, but the electron orbits, say, or shells. Okay, so I wish this little bar wouldn't keep coming up here, but the n equals 1 is that first shell. N equals 2 is the second shell. That's the second energy level. N equals 3 is the third energy level, the fourth energy level, and the fifth energy level. All right, so a transition from like 5 to 4 would release energy. A transition from 4 to 5 would absorb energy. And the amount of energy that's absorbed or released usually corresponds to a color, a particular color. So when you're looking at an emission spectra of a particular atom, what you're seeing are electron transitions from one level to another level. So when you look back at that emission spectrum for hydrogen, when you see that purple line, you're looking at an electron that's moving from the fifth level down to the second level. That blue-green line is an electron moving from the fourth level down to the second level. Right? We have to account again for both the wave and particle behavior of our electrons. We're going to talk a little bit more about how they behave as both. But we can notice in particular the wave behavior of our electrons by using this, what's called the de Broglie relation, right? So we can take a wavelength of light and we can associate it to Planck's constant divided by the mass of the electron in kilograms divided by the speed. Notice how this V is like a regular looking V. That's because it's the velocity. It's the speed in meters per second. Okay, so we can relate either any of these components to one another as long as we have the rest of them. So using this, though, we can actually calculate things like the wavelength of an electron traveling at a specific speed, or we'll be able to calculate the speed of an electron at a particular wavelength, right? That's interesting information to be able to come up with. So let's look at this. Let's calculate the wavelength of an electron traveling with a speed of 2.65 times 10 to the 6 meters per second. Now to do this, you're going to need your de Broglie relation, okay? And you're going to need this value right here, the mass in kilograms of an electron. Now that's not a number that you have to memorize, but find it and write it down, okay? You have to know that when you see the de Broglie relationship that you need this value here. Let me actually box it off for you. Oh, I think I can draw a box. Yeah, there's a box. There you go. So that's the mass of an electron in kilograms. And that is a value that you're going to be using every time that you're calculating the wavelength or the speed of an electron. All right, so this is also one of the cases where it's really helpful to have your Planck's constant broken down into its alternate units, okay? Because what do you have? You have kilograms right here. Oh, look, there's kilograms right here. Now I can see where that kilograms actually cancels out. If you leave Planck's constant in terms of joules times seconds, it is not that easy to see. All right, so we can plug this in and we get a wavelength of 2.74 times 10 to the negative 10 meters. Whoops. So we have proof that electrons act like both waves and particles, okay? Because they basically, I don't know, they diffract both ways. Now, if an electron just behaved like a particle, I know I'm doing these slides a little bit backwards. If you put them through this double slit experiment that we had talked about before, if an electron just behaved like a particle, all you would see is two lines over here, right? One line for each slit, because particles move in straight lines. Okay, so that is the expected behavior for particles. So if electrons only behaved like particles, we would see two bright lines and that would be it. What we see instead is this, though, this mess right here. And we talked about the interference pattern a little bit earlier, but now this is actual electron behavior. Okay, so what that means is that if you have a beam of light and it's going through two very closely spaced slits, instead of seeing just two lit up slits, and you do notice that the center ones are brighter, but you also have this interference pattern. So that means that the light has to be traveling like a wave would travel. Only waves can make this interference pattern. Particle beams cannot make an interference pattern like this. Particle beams don't bend when they encounter an opening. All right. So these patterns here proved that light is behaving as a wave and a particle. Has to be annoying. Electrons always have to be annoying. Think about this question real quick. Okay, since quantum mechanical theory is universal, it applies to all objects regardless of size. Therefore, according to de Broglie relation, a thrown baseball should also exhibit wave properties, not just a particle property, right? Why don't we observe such properties at the ballpark? Okay, I'm imagining that you're reading through this and you're maybe paused to think about everything here. And I mean, this is what it comes down to. Okay, size matters in terms of the quantum mechanical theory. The reason why an electron has a particle nature and a wave nature is because it's so small. Okay, it's so, so tiny. So something like a baseball is far too heavy to be exhibiting a de Broglie wavelength, right? It's going to have more of a particle nature to it. That's why a baseball is going to kind of fly true most of the time, unless it's like kind of windy out or whatever. But an electron is too small for it to behave just one way or the other. All right. We call the wave nature and the particle nature of electrons complementary properties. All right, and we find a few sets of complementary properties in nature. When you have a complementary property, it means that the more you know about one property, the less you know about the other one. So the more we know about the wave nature of an electron, the less we know about that electron's particle nature, and vice versa. All right, this leads us to what's called the Heisenberg uncertainty principle. Now, this allows us to have some kind of relationship between the position of an electron and its velocity. However, over here, these properties are complementary as well, because, you know, it's like speed or position. It's particle or wave. The more you know about one, the less you know about the other. The cat's either dead or alive. It's not both, right? So by finding out information about one of these things, we're going to know less about the other thing. So to use Heisenberg's uncertainty principle, we're going to say that the uncertainty in position multiplied by the mass times the uncertainty in velocity is going to be greater than or equal to Planck's constant divided by 4 pi. Okay, so we can use that relationship to find information about one or the other. So take a second and read through this. Which statement best summarizes the uncertainty principle? Pause this video and actually read this question and try it for yourself. Okay. But I mean, hopefully this answer is obvious. Either the position or the velocity of an electron can be accurately known at the same instant, but you cannot know both of those things. You can know one of those things. Okay. I'm going to pause this for now, just to make the video a little less daunting, and I'll do the rest of it later on today. So listen, fill out your packet, try the questions, and then email me if you have any questions or concerns about the material.